In this video, I want to just go through Chapter 5 and highlight some of the things that you need to pay attention to. So as you can see, Chapter 5 starts with an introduction, and all that I do here is, what we're doing is we're contrasting the language SL with the language PL. The level of analysis that you can achieve with SL is very simple. So you're given this argument down here, and then you contrast it. Well, you don't contrast it, but then you look at the symbolization of that argument up at the top of the next page. And that's the best you can do in symbolizing it. And the thing that's interesting here is that this is obviously a valid argument. The argument is valid, but you can't show that it's valid using truth functional logic. And what we want to now do is develop more sophisticated ways of showing that an argument is valid, or analyzing an argument to see whether or not it's valid. And that requires us to increase the complexity of our formal language. And that's what is begun in 5.2. So let's go to the next page here. 5.2, this is a lot of the stuff that I did on the PowerPoint that I posted on YouTube. So we start with Hypatia is an astronomer. In SL, you just write S. But in predicate logic, we use the letter H, in this case, to stand for Hypatia. And then we use the capital letter A to stand for the property of being an astronomer. And instead of going Hypatia is an astronomer, number 4 here has the syntax, the grammar of the subject Hypatia and the predicate astronomer. We reverse that order. The standard way of doing that is to have the predicate symbol on the left, the individual symbol that stands for the thing that the property applies to on the right. Okay, so it's important to just understand what's going on with the language. There are some technical terms here. Denotation is the thing that the name refers to, the object that the individual constant refers to. There's some vocabulary that's important, and we'll get to that as we move on. And so the rest of this page goes on to give you examples of how to apply to language. Here we call, in the PowerPoint, I called this an informal interpretation. Here in the text, I say I've called it a symbol key. So you can call it a symbol key. It's a kind of informal interpretation. When you say, here's what the letters stand for, here's what the predicate symbols mean, and here's what the individual constants mean. Notice that the variables they're not names. They don't work like the letters A through T. The individual constants are the things that are names of individuals, and the variables are like pronouns, as I've said on that video. It's important to look at 5.1, 5.2 is important. 5.2, page 205 goes through the introduction of the the universal quantifier there on page 205, and then it gives you an example of a whole argument symbolized in predicate logic. And this argument is the same argument from page 200. That's this argument here. And so if you compare and contrast the argument symbolization on the top of 201 with what you get here on page 206, you see that they're very different, the symbolizations. And the thing is, the symbolization on page 206, we can give a formal proof of that. So that was the whole object. The thing here in English on page 200, you can see it's a valid argument. So this is valid. But the symbolization of it, we can't prove. Because if you build a truth table for this, you'll have in the second row, you'll have A true, B true, C false. So on a truth table, it would look invalid, even though the English version is clearly seen to be valid. And so when we make our language richer, we get this symbolization, which says all, ancient astronomers are stargazers. Hypatia is an ancient astronomer, therefore Hypatia is a stargazer. And we're going to be able to prove that because we'll add some rules. We're going to use the rules of proof for statement logic coupled with some new rules that have to do with the quantifiers and the individual symbols. Now, let me get rid of that highlighting here. 5.3 is important it's important to know what the syntax is. The syntax is the grammar. Now there's a lot of complexity here that would be for a more advanced level. In our class, we're just going to use capital letters. We're not going to use these subscripts. We're not going to use superscripts. The reason we have subscripts and superscripts technically is to distinguish the symbol, is first of all to distinguish the symbols from statement letters. So really, really formally, the capital letters, without a superscript, those are statement letters. One-place predicates would have, a number 1 at the top. Two-place predicates would have a 2 at the top. We're not going to do that. It's unnecessarily complicated. We can just use capital letters, and when we give the statement key, like we did here on the left, we put the X next to the A, you can see that capital A is being used as a predicate symbol. Real formally, if we did this completely formally, then when we put the individual symbol next to the A, we'd have to have a number 1 there because it's a one-place predicate. But we're not going to do that. That's more complicated than necessary. Another theoretical thing is just like with statement logic, we had an infinite number of statement letters. We could always attach subscripts. We could go from A to Z without any numbers, then A to Z with a number 1, A to Z with a number 2. We have infinitely many symbols. So for theoretical reasons, it's important to say we have infinitely many symbols available, and we can distinguish whether a symbol is a predicate symbol or a statement letter using the superscripts. But it'll be obvious from what we do from now on whether something's a statement letter or a predicate symbol. And we're never going to use more than a few predicate symbols at a time. We're never going to use we're not going to use 26 of them even, obviously, in any given sentence. So we certainly don't need more than that. All of this business, this shaded box, it looks complicated, it looks a little mathematical. All it says is, there's an infinite number of statement letters, here's the connectives, here's the grouping symbols. We have an infinite number of predicate symbols, as I was just describing. We have an infinite supply of symbols for individuals. We have an infinite supply of symbols for variables. But in practical terms, we're never going to use infinitely many of them. The infinitely many need comes up in more theoretical conversations than we're going to have. And then the quantifier symbols, for all, and for some. Okay. So it's important to get the gist of this. It's not critical. You do need to know the syntax, though, and I'll get to that. That is the grammar. So here, term, any individual constant or individual variable is called a term. And that becomes, the word term just means the thing is a constant or a variable. Using the word term provides a certain efficiency in giving other definitions that come in later that we probably won't get to in a later chapter. I'll usually just refer to individual constants or individual variables separately, or I'll call them constants or variables or names and variables. Then at the bottom here, this is important. Okay, so here in this part, in 5.3, this is something that you need to understand. We define a formula, and a formula is different than a statement. A formula is almost a statement, and I'll explain that. If you restrict yourself just to the language of statement logic, if you're just talking about SL symbols, then a formula in SL is the same as a statement in SL. Formulas and statements in SL are the same thing. It's only when you add individual symbols, and in particular when you add the variables, that you get a formula. Something could be a formula but not be a statement. All statements are formulas in quantified logic, but some statements are not formulas, and that's something that you're going to need to be careful as you read about. So it looks technical. It's just the definition of every, anything you put together using the connectives has one of those shapes. We've already seen that. Now here's the new part where it's a little bit more concerning. And this is something you should study carefully to understand, this part here that I've circled. L formulas. We're all talking about L formulas. If P is a formula and A is a variable, alpha is a variable, then for all alpha, P is a formula, and there is an alpha, P is also a formula. Okay? For all alpha, and there is an alpha called quantifiers, we have the variable of quantification, and then the closure clause here, nothing but what follows from the preceding numbers is a formula. Now, what is this difference between a formula and a statement? Go back to this business here. I didn't say anything a moment ago about clause 2, but it's important. Any n-place predicate symbol followed immediately by n terms is a formula. So let me give you a little pop-up here in Word. So let's use some big letters for you. AA is a formula according to that definition, and so is AX. And each of these is a formula. If we go back to that PDF, any n-place predicate symbol followed immediately by n terms is a formula. Okay, so here, looking at that Word document, here is a one-place predicate symbol followed by one individual term. That's the formula. Here, again, is a one-place predicate symbol followed by a single individual symbol. That, too, is a formula. And as I was saying, if you were doing this like really, really formally to show that this is a one-place predicate symbol, you'd have this little number 1 there showing, this A is a one-place thing, so there's got to be one object next to it. A is a one-place predicate symbol, so there's got to be one object next to it. But to make it easy, we just leave that out because it's not really going to bother us without that there. And these are both formulas. And what comes subsequently is that this first one, this is an example of a statement. That's what A is. The second one, however, is a formula, but not a statement. We'll fix that formula there. It's a formula, but not a statement. And the difference is, in this first one, the letter A appears, and remember the letters A through T are names of objects. They actually name something. X does not name anything. X is just like a pronoun, it, without the reference being specified. So let me, if you were giving an interpretation, you might say AX means X is happy. and A is, little a, is alva. So AA says alva is happy. The X here, in this, when I give this little statement key or informal interpretation, the X here in the interpretation is to be understood just like there being a blank space there, is really all it is. It's just like there's a blank space. It's how you think of it. It's just taking up space to show you that something goes there. Something has to go right there in order for this expression to be meaningful. So AA is meaningful. But this here is just thought of as being, you know, something is happy. It is happy. This statement has a truth value. This formula does not have a truth value. This formula does not have a truth value. So that's why we say that formulas, which have the X's in them, these are not statements. The definition of a statement is, right, a sentence that has a truth value. This does not have a truth value. If I say, tell me, is it happy? Right? Well, I don't know. What is it? We haven't said what it is, so it doesn't have a truth value. It just has a variable. And the fact that I use X here, it could be any variable, actually. I could have used Y or Z. So let's get back to that PDF. So it's important to understand what a formula is, and then we're going to distinguish that from statements. So here are examples of formulas. Each of these is a formula. Those are all formulas. And as I show you in these formulas, these are strictly according to the definition. They have those superscripts. But down at the bottom, I show you, we do the thing without the superscripts. That's how we are going to write them, without the superscripts. And then these are not formulas. They're not formulas because you can't build them using the syntactic rules. Just like in SL, you can't do that. Now, you need to know what a formula is, and down at the bottom, there's this idea of a bound occurrence and a free occurrence of a variable. This is important. You should know what this is. And underneath are some cases, and I go through them on the next page to show you which variables are bound and which variables are not bound. We go through, we take them all up, and then we talk about the scope of a quantifier. So understanding what a bound and free variable is very important, because a statement is a formula that contains no free variables, contains no free occurrences of variables or free variables. Okay. The concept of scope is important. Understand, go through each of these and the discussion here to understand which of these is important, what the scope is, what the scope is not, where the free occurrences are, and where the bound occurrences are of variables. Some more vocabulary here that's useful. But like I say, this stuff here, you know, this is among the most important things in this chapter. This stuff, knowing what a formula is and what a free and bound occurrence is, those are three or four of the most important things here. Okay. I'm going to assign you some different exercises than these probably, or what I'm going to do is I'm going to make this into a quiz, I think. This is easy to make into a quiz because I can just say, you know, put in your answer for number 1, number 2, number 3, and it'll grade your answer as homework, that is to say. A homework quiz, just for practice, not a graded quiz. Okay, formal interpretations. we're going to set this aside for now. A formal interpretation is a little bit more involved, and right now I want to focus on just doing the symbolization. So there's what an interpretation is, and it's more complicated than in statement logic. It's a little bit trickier to say what truth is under an interpretation. It's a little bit more involved, and this is because of the quantifiers. And I'll explain that in another video lecture, not right now. Right now we're going to focus on doing symbolization. So I'll give you some more lecture notes having to do with symbolization. And it's not until you get to 5.6. So what you might want to do now, you can read through the whole thing, and I encourage that if you're up for it. But at the moment, you might want to skip from 5.4. 5.4, let's see, is that right? No, you want to skip from 5.3. Skip from 5.3 over to 5.6. And that's when you get, the stuff that I did on the YouTube video that I posted. The categorical forms, how you symbolize those things, and then the exercises that I'll give you will ask you to symbolize statements using the language PL. And I think it's easier to do that, and then I'll come back to interpretations. There's also 5.7, which has to do with multiple placed predicate symbols. So that's something you want to get on to. And this is interesting, but we're not going to worry about it. Not important for us. So right now, let's see here, 6, 7. So you want to go back to my Word document. For now, starting PL, chapter 5, 5.1, 5.2, 5.3, 5.6, and 5.7. We will return to 5.4 and 5.5 a bit later. Okay, we're just about to start our daily video, so I'm going to stop this and I will be